Imagine training a machine learning model to recognize animals, but then the world changes. New species appear, or the way animals look shifts over time. How does your model keep up? This is the heart of a big challenge in AI, non-stationary data streams. In real-world scenarios, data isn't static. Think of a weather app adapting to sudden climate shifts, or a fraud detection system spotting new scam tactics. Two critical problems plague these systems: concept drift, when the underlying patterns of data evolve over time, and novel class detection, when entirely new categories emerge. Most research tackles one issue at a time, but what if both happen simultaneously? That's where this groundbreaking study shines. Researchers from Rockwell University of Science and Technology developed a synthetic data stream generator called OWDSG. Think of it as a virtual laboratory for testing AI models. It simulates environments where both concept drifts, like shifting weather patterns, and new classes, like undiscovered species, appear. Why synthetic? Because real-world data with these complexities is rare, and synthetic data lets scientists control every variable with precision. The generator uses a tool called Madelon to create static data, then injects dynamic changes into the stream. Imagine a conveyor belt where some items suddenly change shape, concept drift, while new, unknown objects get added midstream, novel classes. The team tested two key tasks. 1. Unsupervised drift detection. Can models spot changes without labels? 2. Open set recognition. Can they identify objects that don't fit any known category? They found that traditional methods often fail when both challenges hit. For example, a model might misclassify a new animal as a known species, or miss a subtle shift in data patterns. But their synthetic streams revealed that unsupervised techniques, which don't rely on labeled data, can catch these changes if tuned properly. This work isn't just about generating data, it's about preparing AI for the real world. From medical diagnostics to cybersecurity, systems need to adapt to the unexpected. By creating controlled environments where both drift and novelty coexist, researchers can build smarter, more resilient models. So next time you see a machine learning model adapting to something new, remember, it's probably been tested in a virtual world like this one. What other challenges do you think AI should prepare for? Let me know in the comments. Ever wondered how machines learn from data that's constantly changing? Like, what if the rules of the game shift while you're playing? That's what researchers call concept drift, and it's a big deal in AI. Today, we're diving into a cool method called OWDSG that generates tricky data streams to test how well AI systems handle these changes. Let's break it down. Imagine training a model to sort fruits. At first, it knows apples and bananas. Then a new fruit, a mango, appears. The model has to decide, is this a new category or just a weird apple? OWDSG creates scenarios where both drifts, maybe apples, start looking different, and novelties, mangoes, happen, testing how well the AI adapts. Here's how it works. The method starts by generating data in a high-dimensional space. Think of it as a complex, multivariable landscape. Using Madelon, they create static data points, then introduce controlled changes. For concept drift, they alter the statistical properties of existing classes. For novel classes, they inject entirely new data points that don't conform to existing categories. This mimics real-world unpredictability. The key innovation is OWDSG's ability to simulate concurrent drift and novelty. Traditional benchmarks often isolate one factor, but real-world data streams are messy. By combining these elements, the generator forces models to distinguish between drifted classes, e.g., apples evolving in color shape; novel classes, e.g., mangoes appearing; concept overlap, e.g., a new class resembling an existing one. Experiments showed that unsupervised methods, like density-based anomaly detection, outperformed supervised approaches in drift scenarios. For novel class detection, models using open set recognition frameworks, like Madelon distance-based thresholds, achieved higher accuracy. This suggests that future systems need hybrid architectures. 1. Drift-aware backbones, e.g., online learning with adaptive weights. 2. Open-world classifiers, e.g., neural networks with uncertainty quantification. This research isn't just academic, it's a blueprint for real-world AI. Imagine a medical diagnostic system that adapts to emerging diseases, or a self-driving car that recognizes previously unseen road hazards. OWDSG gives researchers the tools to test these scenarios rigorously. So what's next for AI in dynamic environments? Should we prioritize drift detection or novel class handling? Let's discuss in the comments. And if you want to dive deeper into the math behind OWDSG, check the description for papers and code links. Stay curious.